I'm live. I'm live. I'm live. Okay. I'm live. I'm live. I'm live. Okay, so I just want to go over one or two examples of like, how does this, so yesterday we talked about what's the energy of a roly-poly, right? How does it affect the answer to something like 12 or 13? 12 you should be fine. I mean, for 12, I'll just give you a little reminder. How do you calculate power? It's asking for you to calculate a power. It's how much energy divided by how much time did it take. So how much energy did you have to input right into the system to get it to do what it did, divided by how long did that take? And that's the power that's the power associated with it. So if you get stuck on that, we can go over it. But I want to just look at like, so 13 and 14 will be two good examples for us. So by the way, let's make sure we all have the same answer for 10, because hopefully we didn't mess that up. But what'd you get for 10C?
5,
6 MV squared, and then D
7/10.
7/10 MV squared. Good. So so by the way, like this is coming up soon, but think about it right now. All things being equal, so let's say this, you have the four most common round objects. You get the hollow cylinder, the solid cylinder, the hollow sphere, the solid sphere. They're all rolling, same mass, same radius. They're all rolling at the same speed. Who has the most energy?
Hollow cylinder.
The hollow cylinder.
Yeah, because yes, you can.
Right. You can think of it like all of his mass is far away from his center of mass, right? So that makes his I value bigger, which thus means he's gonna have more energy. Or just look at the formulas we just derived, right? His formula for rolling kinetic energy is bigger, right? Who's got the least energy? Solid sphere, because he has the smallest I value. Okay. So we all okay with that?
Yes.
Okay. So, like for 13, all you got to do, we won't solve the whole problem, but we'll set it up. This thing is rolling with some velocity. And the question is, how high will this ball go up the ramp? Okay. So what type of argument?
Argument. You do 1/2 mv squared equals mgh.
Close. If this is a frictionless block, I'd say 1/2 mv squared equals mgh. We're using energy.
1/2 mv squared plus 1/2 or 1/2 I omega equals mgh.
1 of I omega squared. Yeah. Well, we could, sure, but we just derived, right, the energy for a rolling hollow cylinder, right? Oh, it says a solid cylinder. Sorry. So a solid cylinder has sorry, really belaboring the point here, but a rolling solid cylinder would have a total kinetic energy of 3/4.
Yeah.
So that's what we got for the solid cylinder, right?
Mm-hmm.
And now we got it from what Colin said. We got it by starting with 1/2 mv squared plus 1/2 I omega squared. The kinetic energy plus the rotational kinetic energy. Now this is the total kinetic energy of this rolling object. Now the thing is, when it reaches the top, it's not moving and it's also not spinning either, right? Up there. So therefore, there's no more kinetic energy. All of that energy got transferred into potential energy. Now they give us the mass on this question, great. But the mass is going to cancel out of our calculation for calculating the height, okay? And then this, if you think about the setup here, who would go higher up the ramp? A solid cylinder like this or say a solid sphere?
Solid. So solid cylinder is smaller. No, really, I think it's small.
Sphere because
it
has the smaller eyebrow.
Let's look at this. The answer is the solid cylinder would go higher. It has more energy. All things being equal, assuming it's at the same speed. Right? So here's the solid cylinder. Solid cylinder. Compare it. Let's suppose it was a solid sphere, for argument's sake. You would have had what, 7/10? It would have been the same calculation, right?
Can I see it?
But which of these would get you a bigger answer? Right? 3/4 is bigger than 7/10.
Yeah.
So this H value would be bigger than this H value. Likewise, look at 14. You know, another problem we've looked at many times with a block, right? So how fast would this thing be going at the bottom of the ramp? We know the initial height is 6. That's a big ramp. Okay, 6 meters. So how much total energy do we have stored up there? MGH. All that energy is going to be converted into kinetic energy down here. Now for a hollow sphere, this is going to be 5/6 mv squared. The m's will cancel out again, but now think about this. If this number, so the bigger this number is, so assuming the height is the same. So let's say you were going to roll down off the same ramp, solid cylinder, hollow cylinder, etc. The bigger this number is, the smaller this is going to be, right? Which we saw that before when we just were talking about how like alpha, the bigger the I value, the smaller the alpha you're going to get. So we've actually already talked about this ranking of who's going to make it down the ramp the fastest. Well, the solid sphere would win the race. And not only that, the solid sphere would have the biggest speed. All right, that's kind of all I wanted to mention. I mean, if you look at like 15, 16, 17, and 18, it's all just kind of following up on that idea of just making sure you understand the idea of like, if you're going up a ramp, for example, the bigger your I value, the more energy you're going to have, all things being held constant, versus over here, the bigger your I value, the slower you're going to be going at the bottom of the ramp. So it's not a super easy thing to wrap your head around, but hopefully it makes sense, or it will make sense upon some further thinky winkies.
Mr. Hall,
What
for 11B,